Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to have Philip Watts here. So he graduated in UCL in 2008. Then he moved to Cambridge, where he was a research fellow at Computer Lab, and now he's back to UCL as a lecturer. So he has been working a lot in optical connections, and today he's going to talk us about his recent work on photonic interconnect and optical switching. Okay, thanks a lot.
Okay, thank you. Yeah, it's really great to be here. So yeah, as Paolo said, I come from an optical engineering background. I spent quite a bit of time in industry designing products for long-haul fiber communications. And then I did a PhD also looking at long-haul fiber communications. So this is trying to send the maximum number of bits per second along, over the maximum distance, say under the Pacific or so situations like that. So actually during my PhD, I came here to Cambridge to work for the Intel Research Center, which was here at that time, sadly no longer here. And I got interested in using optics for computing, for optical interconnect. And so after my PhD, I went to the computer lab, where I wanted to learn more about computer architecture, because it occurred to me that there's a lot of people looking at optical networking as a sort of a black box, not considering sort of applications or what was going to actually attach to the end of to the nodes of this network. And there were people doing some work on some networking on a variety of levels of computing, maybe making assumptions about optics, but they didn't sort of understand optics at the lowest level. So I wanted to work in that interface between the two, and that's what I've been trying to do over the last few years. So as Paolo said, yeah, I spent 3 years at the computer lab working with people like Andrew Moore in the networks group, so John Crowcroft's group, and also with Simon Moore in the computer architecture group. And then I moved back to UCL because I wanted to have experimental facilities in optical communications as well. So I now work for the Optical Networks group at UCL. I've got 5 academics here. Most of our work is still on the long-haul optics, so maximizing bit rates using advanced modulation formats and digital signal processing. We've also got some network, sort of large-scale networking work, like cognitive optical networks, reconfigurable networks for access and long haul. And what I've brought to the team is the interconnect work. But we've got a very well-equipped lab for optical communications. 40 gigabaud, that's probably an underestimate now, and very large transmission distances, or trans-Pacific transmission distances. And although I didn't put it up there, we've also got a lot of expertise in FPGA work, both for DSP and for controlling, for network control. Okay, so starting point, there's a lot of people looking at data center power consumption. These sort of vast data centers almost require their own power generation facilities. They've grown so large now. But looking at the detail, according to Google, only 5% of that power is consumed by the networking devices. And so there's a lot of people looking at optical networks for data centers. And justifying it in terms of energy. But we're talking about only 5% there. And if we look at this study in the bottom right here, which shows this sort of energy profile as we access a cloud device from a mobile phone, we can see here, I hope you can read that the big switches, the core switches, the switches at the top end of the data center hierarchy are actually very efficient, and even the top of rack switch. The energy inefficient points are at the user access end, at the actual mobile phone and access, and down at the server and rack scale. And that's where I've focused my attention on this at the server and rack level. Because this Google figure of 5% doesn't include the networking elements which are actually inside the server itself, and now increasingly actually on the server chip itself, including, I firmly believe, we'll have the photonic components actually on the server chip as well. And of course, a big issue down at the server level is not just the total amount of power you're consuming, but also where it's consumed. There's the power density. So we've reached a situation now where we can put several billion transistors on a chip, but if we try and switch them all at once, it'll overheat. And so this issue of dark silicon is becoming very important. Yeah.
So what is the number? What is the percentage of a server's power consumption that is sort of networking, whatever?
Networking, right. I was just about to come on to that, actually. So yeah, so if we look at a high-performance server, this is a Spark T3, which has got quite a lot of literature written about it, which is why I've sort of used it as an example here. This is a 16-core device. It's got a very large crossbar on chip to connect the cores with the L2 caches, 512 gigabytes per second. Consumes actually quite a surprisingly small amount of the power. But we've also got 1.3 terabits per second for memory, both links to DRAMs and to provide chip-to-chip coherence, because this is designed to work as a 4-socket server with a shared memory across all 4 chips. And we've also got PCI and 2 integrated Ethernet ports on chip as well. And this it's this off-chip interconnect, well over terabit per second, which is consuming 20% of the power consumption in this particular chip, and I would think that's probably typical. So, of course, with devices like the high-speed serial ports and the Ethernet going on chip, I think it's inevitable at some stage we'll also have the photonic components going onto the chip as well, particularly given all the interest in photonic interconnect. So I don't know what sort of level of knowledge people have of these photonic developments, but just to give you a few very brief examples here. In silicon now, of course, silicon uses all the investment that's gone into CMOS, which is why there's so much excitement about it. We can build waveguides at the top there, but very, very tiny waveguides, which can have very small bend radii. So if you bend an optical fiber, you'll start to get losses. Eventually, it'll break, of course. In silicon, because of the refractive index of silicon, we can get very small radii and hence build very small features. Still very much larger than the CMOS transistor, but small compared to any other photonic components that are available. These ring resonators down on the bottom left have attracted a lot of attention because they can modulate, filter, and switch. Some temperature issues with them, but research is looking into those. We can also build photodiodes by integrating germanium into the silicon. The difficult thing is integrating lasers, but people have worked out ways of integrating 3-5 materials into silicon. So, we can put lasers on a silicon chip if we want, or we can keep the lasers off chip and just pump in like a photonic power supply. And we can also build waveguides into printed circuit boards as well. That's another activity at Cambridge. And we can also switch at fairly high rates, 1 nanosecond switching time. Again, slower than CMOS, but still very much faster than other switching technologies. So the only widely used commercial optical switching technology at the moment is things like liquid crystal, piezoelectric control, or MEMS devices, which switch very slowly. So these are ideal for circuit switching, for reconfiguring a system and leaving it in that state for a long period. But if we want to do anything on a shorter time scale, like packet switching, or setting up very short scale circuits for shared memory, we need a much faster switch. And there are a number of candidates for this which have been researched. We've got semiconductor optical amplifiers on the left here, which if we switch the amplifier on, we sort of pass the light. If we switch it off, it absorbs the light. So we can build a two-port switch by splitting the light and switching one or other of the amplifiers on, or both of them if we want to broadcast. Mach-Zehnder interferometers are another option. Very, very, very fast. They've got some crosstalk issues. And also the ring resonator that I just mentioned can be used for switching. And this is a little difficult to understand. Basically, if the ring is in resonance, that means it's a whole number of wavelengths. Light is taken from the horizontal waveguide there onto the vertical waveguide. And we can change the resonance by changing the refractive index of the ring. I won't go into that too much. I can explain it more afterwards if people are interested. So we have lots of exciting developments going on in photonic integration and silicon photonics. And there's a couple of concepts we've been looking at in our work at UCL. One is for shared memory. I got interested in shared memory when I was working with the computer architecture group at Cambridge. So if we have this sort of multi-socket server, rather than having this two-layer interconnect of an on-chip crossbar or mesh network and an off-chip, a chip-to-chip network, which is done in electronics because there's a fundamental difference between the off-chip wave transmission lines and the on-chip wires. We can build a single network which could interconnect all the cores through some sort of optical switch and give us effectively a single hop connection between any cores. The challenge there, of course, is how do you set up those connections, and that's been the subject of our research. I'll come on to that in a minute. The other thing we've been looking at on the rack scale rather than the single server scale is to replace the top of rack switch, sort of this sort of traditional leaf and spine data center hierarchy with an optical switch, and have devices, the transmitters and receivers integrated onto the server chip, so we have no other devices in the path. Again, we've got direct server-to-server connections within a rack, two-hop connections between any server in the data center. And this is only one possible topology you could use, of course, but it's kind of an obvious way of inserting an optical switch into this arrangement. And it has a number of advantages. We can get very high bandwidth. This helps to overcome things like incast issues. We don't have the same sort of pin and front panel bandwidth issues we'd have with electronics. And the arbitration problem, again, comes down to can we set up the connections fast enough, is relatively tractable if we're just talking about providing enough connections to connect the servers and some uplinks to the spine switches. 64-port optical switches. Actually, 128-port switches have now been have been demonstrated in an integrated chip. So those are the two concepts I'm going to talk about, the shared memory network for a single chip or multiple chips, and this optical top of rack. So as I've just mentioned, the challenge here is can we, given that in shared memory we're dealing with very short packets, the challenge becomes, can we set up these connections fast enough? So we have lots of nodes connected to an optical switch. This is a very sort of traditional switching arrangement, and we don't do anything too clever. The latency is determined like this. We need to send some sort of request to the switch controller. There's some sort of arbitration process has to take place, and then we give permission to send. Of course, this process goes on within an Ethernet switch as well, but that's all contained within a single device. If we want to use photonics effectively and put our signals into the photonic domain on the server chip, this is going to become a sort of distributed problem where the switch and the nodes are separated at least by a few meters. We've then, obviously, there's some time of flight for the signals to reach the receiver. And then, of course, the serialization latency can be very low here because we can generate very large bandwidths optically. Synchronization latency means we need to recover the clock. We need to have the same clock between transmitter and receiver. We're looking at that problem, but I won't talk about it too much today. So what I'm really going to focus on is this process of setting up the optical paths on the switch. Just before I start on our work, I'll just give you a brief overview of some of the ways that other people have looked at this problem. So on the top left here, we've got speculative transmission, in which we send a request to the switch controller, and very shortly afterwards, without waiting for reply, we send the data. So if the arbiter can find a path through the switch, then the data goes straight through to the receiver with very low latency. If it can't find a path, the data is either dropped or rerouted in some way. People have looked at optical methods of arbitration. It tends to involve very sort of complex optical schemes. HP did some work in this. And then a lot of groups simply try and avoid the arbitration problem altogether by using a different optical topology. So on the top right here, you can see this scheme proposed by Oracle. They've decided that optical switching is just too far away or too difficult to do. And so their approach is simply to use the bandwidth that you can get in optics. We've got space and wavelength dimensions to play with, and create an all-to-all network. So we connect every node with its own individual connection defined by either space and wavelength. And of course, this means you need n-squared transmitters and receivers. An alternative, which is slightly less complex, is this single writer, multiple reader scheme. The first time I came across this was the Firefly project at Northwestern University, but this has become very popular as a topology for networks on chip and sometimes for larger scale optical networks as well. Here we have n waveguides, optical waveguides. On each waveguide, one node is the transmitting node. All the others are listeners, and they listen for communications that are intended for that node. So again, we need a lot more receivers in this case than we would in a conventional switch. So these are sort of two ways, the all-to-all network and the single writer multiple reader, two ways of avoiding the arbitration problem by increasing the complexity of the optical network. So By comparison, in our shared memory work, we've done some work on arbiters. Actually, we can do arbitration even for quite a large number of ports, like 64 ports in a few nanoseconds. We know the latency is very critical for these shared memory systems. But also at this level, on the level of a single server with a shared memory, the communications is also very predictable. So our approach is to keep the central switch, keep the arbiter, but try and use it as little as possible, as much as possible. Try and predict the communication that's going to take place in this shared memory system. So I'll just briefly describe what the traffic looks like on a shared memory system. I don't know how familiar people are with this. So here we've got a number of processors on this interconnection network. They've each got a private L1, some proportion of a shared L2, and the directory associated with that block of memory. So they each control a block of memory, and they have the directory co-located for that block of memory. So if core 0 here wants to access a memory controlled by core 3, is this going to work? Yeah. It first needs to send a request message, and this is quite a small message, just 8 bytes. That goes to the directory. CPU 3 then realizes that that data is also already has been given exclusive access to this CPU N. So it has to send a message to CPU N, again, just a short control message. CPU N invalidates that data in its cache. And then the present state of the data is sent back to the requesting node. That's inserted into the L1 cache. And then an acknowledgement message goes back to the node that has the directory. So you can see most of the communication here is in terms of very short messages, and optics, which is naturally a sort of circuit switching technology, might not be the ideal communication medium here. But also the communication, there's only a certain number of transactions we can carry out on this. I mean, the simplest ones are load requests and write requests, in which there are no other sharers. And you can see here that these just can be met by having a bidirectional circuit. So when the initial request is made here in the load request case, we know straight away that there's going to be in the near future a data response message. In the write request, we also have this unblock message, a kind of acknowledgement message. And so if we set up a bidirectional circuit here, we can avoid the arbitration process for the subsequent messages in this transaction. This is quite a simple idea, but it turns out to be very powerful. And a bit later on, I'll show you some of our work looking at predicting more complex transactions, and also predicting the first request message as well. But this, just applying this simple method of setting up bidirectional circuits when an initial request is made, actually turns out to be very powerful on its own. So we've run the parsec benchmark in Gem5 and looked at the traffic patterns within there. We can save about 60% of the arbitration latency on average across the benchmark, irrespective of how large the network is. So if the time of flight if we've got a network on chip, the time of flight between the switch and the nodes is just going to be 1 or 2 clock cycles. If we've got this multi-socket server, it could be up to 10 clock cycles. But we have the same average saving. And what that means is that the load on these networks is actually pretty low. So we don't get a lot of contention. Because you'd expect, if you set up these bidirectional circuits, obviously the longer the time of flight, the longer the circuits have to be. But this linear relationship basically shows that the load on this network is low enough that these longer circuits don't interfere with other traffic. So this graph is in terms of the arbitration overhead. In other words, that the number of clock cycles it takes to set up the circuit. It'd also be useful to compare this scheme applied to the basic sort of optical switch with these schemes that don't which avoid arbitration by such as the single writer multiple reader scheme. So in our assumed case, we've got this broadband switch. We're going to send 160 gigabits per second per port. It's 16 wavelengths at 10 gigabit per second. It's fairly conservative, really. But we found we don't need more bandwidth than that, actually, in this case. We've shown that through the Gen 5 simulations. And in this case, we need 16 transmitters for each port. We need the switch and the arbiter. By comparison, in the single writer multiple reader case, we've got we need a lot more transmitters. So we could put 16 wavelengths onto every node, 16 wavelengths of bandwidth onto every node. But this would mean we'd have an extremely large number of transmitters and receivers. So in practice, people are looking at these single writer multiple reader networks are assuming that you'd only have a small number of wavelengths. So the serialization latency is a lot lower in this case. But on the other hand, you get reduced or eliminated arbitration latency on the right-hand case. Yeah, sure.
The one on the right.
Yeah.
Does that lead to more efficient broadcast? Because some cache coherence protocols, like Intel's, use broadcast.
Yeah, that's right. It does depend on that. So we're using a directory protocol, which it doesn't use broadcast. But I know, broadcast would be a very useful thing. It really depends on how you're doing the receiver here, actually, as to whether you can broadcast. I mean, I've portrayed the receivers as being ring resonators here. So with ring resonators, actually what you need to do in this case, which I didn't mention, is basically tell a specific receiver to expect a communication. You need this reservation scheme, actually. Because the ring resonators can either be on, in which case they take all the optical power into their node and don't leave any for anybody else. Or they're off, in which case the power continues along the ring. They can't be half on, because they're resonant devices. They can't be half on or extract 10% of the power. So actually, you have to tell, say, node 2 to expect a communication from node 0. If you could rearrange this and use splitters to effectively send power to all, to broadcast. In which case, you would be able to do a broadcast. But then, of course, you'd have to actually transmit n times the optical power as well in that case. So, either way you do it, you're kind of limited by the sort of power and complexity. Yeah. Does that answer the question? Yeah, great. Yeah, so this this shows the performance in terms of the average memory access time for the crossbar switches. The first two set of bars there are for the central switch for each of the parsec benchmarks. And these are for the single writer multiple readers with 1 to 4 wavelengths. And we've referenced everything to the single writer multiple reader with 1 wavelength. And you see, I mean, the variation, there's a lot of variation in terms of, between the benchmarks, in terms of the speed up in the memory access time. But the key thing to note here is that if we look at where we're arbitrating per memory transaction or memory sequence, we get about 15% speed up. And in order to get the same performance from the single writer multiple reader, you need 4 wavelengths per port. However, if we look at the power consumption, because of the additional receivers and transmitters we need, that network with the four wavelengths actually consumes considerably more power. So we're getting the same performance with less power, less complexity. Oops, something. Or we can get better performance with a small decrease in power compared to the 1 wavelength case. Okay, so I'll just describe some of the other work which is currently ongoing. Because obviously this bidirectional circuit idea, it's actually quite simple. We can go much further than this. So one of the things we're working on with Columbia University is trying to predict that first request message. So before it's actually issued by the processor. So if we look at the results for the bidirectional case, here we've plotted for each of the parsec benchmarks the proportion of circuits which require no arbitration step if we just leave the circuits open. So when a memory transaction is completed, if we leave the circuits open, we're basically we're trying to exploit the locality by basically predicting that the next transaction will be to the same node. And that turns out to be very successful, particularly depending on the benchmark, that is. In the case of VIPs, 70% of memory transactions require no arbitration step if you leave the circuits open. You can also see, again, as I said before, how low the contention is on these shared memory networks. Less than 2% of transactions actually experience contention. But the question is, can we make a better prediction? Okay, we get a really good result here in terms of VIPs, but if we were running swaptions, we're only right with this prediction that the next core will be the same one as last time. We're only right 3.5% of the time. So with Columbia, we're looking at similar techniques that are used in prefetchers actually to try and make a better prediction. So when a memory transaction is finished, do we leave the circuit open, or is it better to, based on a knowledge of the algorithm and patterns that have gone before, is it better to change to a different circuit at that stage in anticipation that a new transaction will use a different circuit? So that's one of the things we're working on. Another thing which we're just sort of writing a paper on at the moment actually is predicting more complex transactions, because I've just described this algorithm which uses just 2 core transactions. But of course, if we need to invalidate memory blocks because they're being shared, we have more complex memory transactions which involve 3 or more cores. And for this, we've looked at a method of misprediction. So tile A in this case, in the top left-hand corner, which is a store requests with an invalidate. Core 1, looking based on previous experience, can predict with quite a high level of accuracy, actually, over 80% in most benchmarks, can predict that there will be a miss in the L2 and can therefore set up some of these other circuits in advance, which gives you a further decrease in the arbitration latency. Okay, so those are things we're working on in the shared memory case. So one thing I'm very interested in here is having a unified network for on-chip and off-chip. I think that'll give us a big advantage over the sort of two-stage networks you see in that Spark server and many other servers. But also looking at whether we can make efficient, larger shared memory systems using these ideas. Of course, you can't get rid of the extra time of flight if you keep adding nodes to the shared memory network over multiple chips. But we can at least minimize the arbitration latency sufficiently that the latency will be dominated by the time of flight latency. Of course, driven by the large bandwidth, we can reduce serialization latency as much as possible as well. Okay, I'm going to go on now to the other scenario which we've looked at, which is the top of rack switch. So in the shared memory network I've just been describing, of course, we've shown a way of reducing the need for arbitration as much as possible. But there will always be situations in which we still need to carry out that arbitration process. And also, if we look at networks on larger levels, like the Ethernet network, which is going to interconnect a data center, the traffic is going to be maybe much less predictable. I mean, maybe there are ways of predicting it, but it's going to be less predictable in the shared memory case. So we need ways of being able to carry out arbitration as rapidly as possible. And the other thing we were concerned about here was actually as I mentioned at the start, the power density issue on the server chip itself. Because of course, as we put more functionality onto the server chip, such as like the Ethernet network interface is already going on chip. As we start to put the photonics on chip, of course, all those functions add to the power density problem of the server chip. So what we tried to do here was build a top of rack switch which has both low latency and also has a very simple server-side interface to get the minimum power consumption, to try and push the complexity into the top of rack switch. So we started off with a virtual channel switch as a baseline. So in this case, we have we queue our packets in the transmitter by output port, by output port destination. We send requests to the top of rack switch when we want to send. Switch arbitration is carried out, and then the grant or permission to send is sent back to the server. Of course, this is relatively slow process that we want to avoid. We also found in our work we've characterized a lot of these control plane elements that that are required for this. We've done ASIC synthesis on these components, like the arbiter or allocator, the controllers you need on the server side. And we found that a really large part of the power is actually in these FIFOs, in the buffering that we need here. In fact, well, you can see that from this sort of power, the power chart at the bottom left here. So this shows at loads from 1% to 60%, the sort of distribution of power that's consumed on the processor chip. So we're not looking at total network power now. We're looking at specifically at the power consumed on the processor chip itself. And the adapter, the sort of turquoise bar there, is significant, and also it can't be power gated. So it's the same whatever the network load. We can't do a great deal about the SerDes, because if we're going to operate at high bit rates, to use the advantages of optical communication, that's kind of inevitable source of power consumption. Although it is actually you can gate that, so that will be an energy proportional source. Another thing which isn't energy proportional is the actual optical power. So as we pump optical power into the chip, that power is going to be absorbed on the chip and contribute to the thermal problems. And that also is a significant proportion. And then we have the transmitters, very, very small, and also able to power gate them, and the receivers, which are shown here, not power gated. There are ways of power gating the receivers. It tends to involve increased latency, though. So we've characterized a lot of these components using ASIC synthesis. We're trying to get these control planes up and running on FPGAs at the moment. And yeah, so we should be able to do a lot better than the virtual channel switch. So the scheme that we came up with, we published at OFC this year, basically has a very simple server-side interface. And contains electronic buffers in the top of rack switch. So we're going to use electronic buffering because it's much more dense than any sort of optical memory that exists. And we're also going to use wavelength striping, as I described before, in order to maximize the bandwidth and give us low serialization latency. So the scheme works like this. We have this simplified, what we call send and forget interface. So as soon as data comes into the FIFO, we send that straight away. We send a request to the allocator. It's like a speculative scheme. And then we send the data. We don't wait until we know that there's a switch path available. So we send out the whole packet on this wavelength stripe format, slightly behind the request on the control plane. Yeah. So it's speculative transmission is attempted. Of course, if there's a switch path available, the data goes straight through to its intended receiver. If it fails the arbitration process, it's routed to these electronic buffers at the top of rack switch. So this avoids the complexity of buffering in the transmitter and pushes that complexity into the top of rack switch. And another advantage of this is when we retransmit those failed speculative packets, they are stored close to the switch. We also give priority to the buffered packets over new packets in the allocator, which maintains the ordering of packets, if that's important, in the application. Also, we found when we were characterizing these control planes that if you need reordering buffers, that is a very significant power source, far more than the transmitter buffering, because they have to be, you need sort of special access arrangements to the memories. So just to summarize the latency here, you can see the baseline VC switch on the left here, with its sort of control delays due to the request, allocation, and grant process. So I've put allocation on sometimes here. When I say allocation, it's the same as arbitration. So it's I've used the two terms interchangeably. Once the grant is sent, then data can be sent through the switch. So in the send and forget interface, we send the request shortly followed by the data. If that's successful, we get much lower latency. If it's unsuccessful, we have to go through the arbitration process again, and the data is sent at a later time. So that's one side of it. That's the low latency side of the scheme. But the other side is reducing the the send and forget interface also gives us lower power consumption because of the simplified interface on the server chip. But also we want to reduce the optical power. And for that we need to look at the actual optical switch itself. So I've shown you this before, the three types of fast optical switches we have. In the SOA, the amplifier case, we can overcome losses using this by not just giving us a transparent path, but actually providing amplification in those SOA elements. But it also produces noise as well, inevitably, which affects your ability to cascade the switches. Both the Mach-Zehnder and the ring resonator switch introduce some losses into the switch path, which if you try and cascade a large number of elements, mean that you have to end up having to transmit a much larger power. So here, if we have an off-chip laser going through the first server chip where the transmitter is, going through the switch chip, and then onto the receiving chip, you can see if we have one of the passive switches, the Mach-Zehnder or the ring resonator, say with 10 dB loss, that's quite low actually for most switching, sort of large-scale switches. We end up having to transmit a much higher power than if we use a switch with gain, the semiconductor optical amplifier switches. And all that additional power is going to be absorbed onto the chip and contribute to the thermal problem. But we needed a switching architecture which gave us the low loss, but also gave us a good sort of crosstalk suppression and was scalable to a large number of ports. And so we've been working with the people in the engineering department at Cambridge. They've developed this switch which combines Mach-Zehnder elements with the semiconductor optical amplifier switch, and it works by creating an array of these 4-port switching blocks shown at the top there into a sort of multiple stage switching fabric. And they've demonstrated that this can scale to 128 ports. And this is with integrated switches. So what they've built at the moment is actually an 8-port switch. But then they've done experiments to sort of cascade these elements to show that it will scale up to 128 ports before noise degrades the signal. So specifically for this buffered switch architecture, we looked at two schemes. One uses 2 of these sort of N-by-N switches with input and output switches. It's more flexible, but uses more of the 4-port switching blocks than the other case we looked at. Not quite so flexible in the way that it deals with requests, but it's simpler in terms of of the number of optical elements involved. And just looking at the speculative transmission scheme that we use, so this is without taking into account any sort of contention. You can see here we get much lower latency on the using the speculative scheme, our proposed scheme, that's the blue and the green lines, than with the VC switch here. And again, I've plotted this over several meters to show we could use this scheme for the shared memory communication as well, where we'd be working down at sort of tens of centimeters, or for the top of rack, which scale to a few meters. If we take contention into account, we get some quite interesting results here from our simulations. So if we use uniform traffic, as you would probably expect, the VC switch does give you a higher saturation load. This is using a single stage of arbitration. At the expense of extra latency, you could push the throughput of the VC switch even higher. But of course, you get higher latency at low loads because it's got to wait for the grant to come back. But there's particularly in the case one switch, the more complex switch, it's getting pretty close to the throughput of the VC switch with a single round of arbitration. But the interesting thing we found was when we used different traffic patterns, such as streaming traffic between two ports with random traffic on the other ports, or incast traffic, which we were particularly interested to look at because this is a big issue for in data centers, and a higher bandwidth optical switch should give you advantages there. In these two cases, the stream and the incast, actually the speculative top of rack switch actually gives you better performance across all loads compared to the virtual channel switch. And this is due to the effect of keeping your failed speculative packets near to the switch itself. So in terms of the power consumption, we get a considerable reduction in the power consumption on the server chip itself by using this combination of the simple interface and the Mach-Zehnder SOA switch, which is the case shown on the right there. You can see at 30% load, we've reduced the optical power and the network interface power to almost negligible levels, really. So the bulk of the power is the receiver and the SerDes, which are so difficult to power gate, difficult to eliminate from the scheme. And you can see in terms of, if we separate this into dynamic energy and static power, it's the static power, the non-power gateable sources that we're really making a big reduction in. In terms of total network power, actually, it's interesting that if we use say a ring resonator switch or something like that, we get very poor energy proportionality, very similar power across the whole range of loads. And this is because we need a high optical power, which is in order to overcome the losses of the switch. Using a semiconductor optical amplifier switch, we actually get very good natural energy proportionality, because the SOA is one of the highest power components in the system. And when we don't need the switch path on, we get extremely low power, negligible power, really. So you can see that there is a small total energy penalty for using this buffered, the recirculation top of rack switch, particularly at high loads. But we get there's a small penalty at high loads for using the recirculation switch. This is because more SOA elements need to be switched on in total compared to the basic VC switch. So it's a question of where we actually dissipate the power. Do we dissipate the power on the processor chip in the VC case, which gives you this power density problem, or do we dissipate it elsewhere in the top of rack switch, which was one of the aims of the recirculation case. Forgot to use those. Okay, so I've sort of presented two sets of work here. One was on the shared memory case, looking at eliminating or reducing the need for arbitration by using prediction, and then this optical top of rack switch, which uses a speculative technique to reduce latency, and this Mach-Zehnder SOA switch in order to reduce the power consumption on the processor chip itself. And at that point, I'll stop. Thank you for your attention. Okay.
Okay, if not, we can, thanks again.